Okay, now we're going to do the last 4 problems, and we're going to look at a little bit now into mechanisms, intermediates, molecularity, and figuring all that stuff out. So we have here a reaction that involves the conversion of ozone into oxygen, right? And so it's been proposed that this process happens by a 2-step mechanism, that ozone decomposes to produce oxygen and O, and then a second ozone molecule reacts with that O atom and produces 2 additional oxygens, right? And so we want to describe the molecularity of each of the elementary reactions in that mechanism. What is the overall equation? And then what are the intermediates in that reaction? So the first reaction, right? So if we look at A, the first reaction is just simply the decomposition of ozone. So I have 1 molecule as a reactant, right? So reaction 1 is unimolecular, right? Just a simple ozone decomposition. So that's a unimolecular reaction. The second reaction has ozone plus O. So there I have 2 molecules. So my second reaction, bimolecular. Okay. So my first step is a unimolecular reaction. Second is bimolecular. The overall reaction, so if I add these 2 reactions, right? So if I have ozone going to form O2 plus O, and then I have ozone plus O to give me 2O2, right? If I add all of those up, right, ozone and ozone gives me 2 ozones plus O, and then I produce O2 plus 2 O2s gives me 3 O2 plus O, right? And so looking at that reaction, I can see that I've got O on both sides of the reaction in equal amounts, right? And so it can be eliminated from the net equation, right? So we'll cross those out. So my overall net for this process, 2O3 goes to form 3 O2s, right? So that's my overall reaction. And the last part of that is then identifying the intermediates. Well, my intermediate is my O, right? Because the O, right, and that's an O, not a 0. My O, it's not an original reactant and it's not a final product, right? It's formed in the first step and then consumed in the second, right? So that's what makes it an intermediate. The fact that it's consumed in the first step or produced in the first step and then consumed in the second step, right? So that's my intermediate molecule. All right, how about predicting the rate law for an elementary reaction, right? So here we have an elementary reaction, right? Elementary reaction, right, says that it occurs as a single elementary step. Hydrogen gas plus bromine gas gives me 2 hydrogen bromide molecules, right? And so this reaction is bimolecular. It involves 1 molecule of oxygen, 1 molecule of bromine. And so a simple single elementary reaction. It's first order in respect to hydrogen and first order with respect to bromine, right? So we say that the rate is going to be equal to our rate constant times hydrogen times bromine. Okay? Right? That is our rate law. That's what we would predict, right? Because it's a single elementary reaction. So elementary, it occurs in 1 step, right? So if it's a 1-step reaction, 1 molecule of hydrogen, 1 molecule of bromine, it would be first order in each, right? Interestingly enough, though, that experimentally, right, we find out that the rate is equal to the rate constant times the concentration of hydrogen times the concentration of bromine raised to the 1/2, right? And so the experimental rate law is different than what we predicted when we assumed it was a single elementary reaction. So what we conclude from that, because our experimental rate law doesn't match up with our predicted rate law, is that it's not a single elementary reaction. It has to involve 2 or more steps. Okay, so when our experimental rate law doesn't match up with our predicted, then it's not a single elementary reaction, that it's actually a multi-step process. Okay. So when we have a multi-step process, right? For example, in this example, we've got the decomposition of nitrous oxide, right? It's believed that this reaction happens in 2 steps. The first step being a slow step, N2O producing N2 and O. And then the second step being a fast step, N2O plus O produces N2 and O2, right? What would be the equation for the overall reaction? Right. Well, for the overall reaction, we would add those 2 reactions, right? So if I have N2 going to form N2 and O, and then I've got N2O plus O going to form N2 and O2, right? If I add those, I get 2 N2O plus O, gives me 2 N2s plus O2 plus O, right? And again, I have O on both sides of the reaction in equal amounts, so we get rid of that, right? So my net overall reaction, 2 N2O producing 2 N2s plus an O2, right? So that is the net overall reaction for that, right? And then to write the rate law for that reaction, right, to say, okay, now we want to write the rate law for that reaction, right? We would say, well, if we look at that reaction, 2N2O going to form 2N2 plus O2, right? Our rate law is based on our slow single step, right? The slow rate determining step, right? Because if it's a multi-step process, the rate law is dependent on the slowest step. Well, our slowest step is a unimolecular reaction. Right. So if it's a unimolecular reaction, that's a single elementary reaction, right? And it's unimolecular, so that would be first order. So our overall rate is equal to K times the concentration of N2O raised to the first power, right? So that would be our first order rate law for the decomposition of N2O, right? Even though the second step is bimolecular, the first step is the rate determining step, and so that's where we get our overall rate. Okay? That's if we have a slow step initially, right? Say we have a fast initial step, right? And then the second step is the slowest, right? How do we produce a rate law for that, right? Well, in this case, I've got a rate, right? Now I'm looking at NO plus NO, right? And that ends up producing N2, reacting with Br2 to give me NOBr2, right? This equation that I'm looking at, I have my fast step and I have my second step, okay? So when I look at this overall reaction, right, we want to look at the overall chemical equation, right? I've got NO plus NO, right? So my N2O2, that's my intermediate, right? Because it's here, it's produced, there it's consumed. So we're going to say 2NO plus Br2 goes to form 2NOBr, right? That's my overall reaction. That's the net, right? And this is a termolecular reaction, right? And a termolecular reaction, we're going to say, occurs in multiple steps. So my second step is my rate determining step, right? And so the overall rate for my rate determining step is going to be the rate equals K2, because that's the rate constant for the second reaction, times the concentration of N2O2 times the concentration of Br2, right? Which is great, right? But what's the problem with that? Well, N2O2 is an intermediate, right? We don't have the concentration of intermediates, right? So we have to solve for the concentration of the intermediates. So we have to get the concentration of N2O2 in terms of either one of the initial reactants or the products, right? Because the N2O2 doesn't show up in my net equation, right? So we have to isolate that, right? And get that concentration. Well, if I look at my first reaction, right, I've got a forward reaction and a backwards reaction. And so the forward rate is equal to the backwards rate. My forward rate is going to be right? So K1, that's my forward rate times the concentration of NO squared, right? Because it's NO and NO, so it's bimolecular. That equals the backward reaction, which is K minus 1, times the concentration of N2O2, right? There's my intermediate. So solving for the concentration of N2O2, that equals K1 divided by K minus 1 times the concentration of NO squared. Right, so that's my concentration of NO2 or N2O2. Now I can take this, plug it back into this equation, right, and figure out what my concentration is, right? So I say rate, we said rate was equal to K2 times N2O2 times the concentration of Br2. And then from my fast equilibrium, N2O2 was equal to K1 times K minus 1 times the concentration of NO squared, right? So if I take this and plug it in, I get K2 times K1 over K minus 1 times NO squared times Br2. Right, so that's my plugging that in, but then this simplifies, right? K2 times K1 divided by K minus 1, right? That we just simplify to K, right? It's a constant. That constant times concentration of NO squared times the concentration of Br2, right? So there we go. There is our rate. Now it's dependent on my initial concentrations of my reactants, NO in the first step and the concentration of Br2 that's present in the second step, right? So the mechanism does yield a rate law that's consistent with the experimental one, right? And there are sometimes maybe more than one mechanism that leads to an observed experimental rate law. Right, so kinetics are fun. All right, that's the end of the practice problems for Chapter 12 in kinetics. So thank you again for watching and enjoy the rest of your day.